Okay, we're going to continue working on 6.1. This video is finding the area between two curves. So we're going to actually put into practice what we discussed and where we formulated the area between two curves, f of x and g of x, as an integral. So let's start with an example. This is a basic example where we're given two curves. So we're going to find the area bounded by y equals e to the x and y equals x squared minus 1 for x between -1 and 1. So we're given an explicit region in the coordinate plane. And here I have represented both of these curves for x ranging between -1 and 1. Here's e to the x, and here is x squared minus 1. Your classic parabola shape and zoomed in exponential curve. And this red line here represents the infinitesimal slice that we're going to be adding up, integrating, really. Okay, so this infinitesimal has area e to the x minus x squared minus 1 dx. Okay, and when we integrate this, so ranging from -1 to 1, we're going to get the full integral that this actually is going to be. Okay, so our work begins here. Now, you may be given the graph, you may not be given the graph. Here I'm going to be providing the graph, but if you're ever in doubt, go ahead and use a graphing calculator as you wish, because it will be important to make sure that the upper curve comes first. Okay, so in this case, we don't have to worry too much about whether we're going to get multiple integrals or finding points of intersection or anything like that. That will come in a later example. So for now, we're just integrating this expression here. And that means finding the definite integral of e to the x minus x squared plus 1. Now, e to the x, that's going to be a simple e to the x. That's the integral of that. Negative x squared, remember that the power rule for integrals means that we're going to get x cubed over 3, and then 1 becomes x. And by the fundamental theorem of calculus, part 2, then we're going to need to evaluate this at 1 and evaluate at -1 and subtract. So I'm going to continue over here. Continued. The area is going to be e to the 1, which is just e, minus 1 cubed over 3 plus 1 minus e to the -1 minus -1 cubed over 3 plus -1. And just make sure that you're following your orders of operation. So e to the 1, remember that's just going to be e minus 1/3 plus 1. Distribute the negative there, so minus 1 over e, because that's what 1 over e means, e to the -1, minus 1 over 3. Now carefully there's a minus sign here, a minus sign here, and then this negative sign here. So the 3 preserves the negative sign, which then if you have an odd number of negative signs, that means you have a negative in the end here. And then plus 1, because there's going to be an even number of negatives there. All right, so combine like terms. Remember the e and the 1 over e, we can't actually combine those, but anything that's just a regular number, as it were, so no powers of e involved, negative 1/3 and 1, and then negative 1/3 and 1 there. So we should end up with, and you can check your pause here and, do the fraction algebra if you would like. It's going to be e to the negative 1 over e plus 4/3. And that's our answer. Okay, that is our answer. So basic example, we do get a real number that is going to be positive, and that represents the area bounded between these two curves. Okay. So let's do another example. This is going to be a little bit more involved. Whoops, I need to add another page. Okay. So example. And in this one, we're going to need to find points of intersection. When we say points of intersection, we mean the two curves are going to cross at some point, and we will need to find that point at which they cross. Okay, so the problem here is calculate the area bounded by y equals 8 over x, y equals 2x, and x equals 4. Okay, so we don't immediately know what this should look like, but I'm going to draw in the coordinate graph. Okay. And here's, we're going to say this is 2 and this is 4. That's going to be 2, 4, 6, 8. The scaling is a little different, so don't mind that this is actually slightly squished. But the upper curve will look roughly like this. So y equals 2 to the x, that should look like, it's going to cross this point and this point. So I've just made it look like that. Okay, this is y equals 2 to the x. And we don't know what the other one will look like, but we do know that if you plug in 1, you get 8, so it should look something like this. And of course, our boundary here, we said that we want to go no further than x equals 4, which means our area, the area that we're looking at here, is this triangular, almost triangular shaped region here. Okay, so the important point here is, what is this point? And I know that I've made it look like it's 2, but we don't actually know that. So we should actually check. So what is the left endpoint? That's the question. So step 1, find the left endpoint. And we can do that by setting the two curves equal to each other. So we're going to do f of x equals g of x. So that's going to be 2x equals 8 over x. Multiply both sides by x. So you get 2x squared equals 8. Divide both sides by 2. And give you x squared equals 4. So this suggests that x equals plus or minus 2. And of course, we don't actually care about negative 2 because that's on the other side of the y-axis. So really what we need here is x equals 2. Okay. So the area here actually, if we look at, we're going to set up the, here's the infinitesimally thin slice, roughly. So the height of that slice is 2x minus 8 over x. The width is dx. Let me write that in. So 2x minus 8 over x dx. And we're going to integrate that from 2 to 4. So our area is going to be the integral from 2 to 4 of 2x minus 8 over x dx. And we're going to use an assortment of power rules here, okay? So first of all, 2x, that's going to turn into x squared. So the integral of 2x dx, it's going to be 2 times x squared over 2, and that's why the 2's cancel. So we get x squared minus, and then 8 over x is going to be 8 times ln of x. From 2 to 4. Now, we don't actually need to worry about the absolute value bars here because we're talking about only positive quantities in the first place, so you can safely ignore that. Now, let's do the calculation. So we have 4 squared minus 8 ln of 4 minus 2 squared minus 8 ln of 2. Notice that these are all powers of 2. And if we cleverly use our logarithm rules, then we can combine these easily. So 4 squared, 16, minus 8 ln 2 squared, minus 4 plus 8 ln of 2. Okay, the whole point here is I'm gonna want to represent everything in terms of just a pure number, or ln of 2, multiple of ln of 2, I should say. So I'm going to end up with 16 minus 4 is 12, minus, by the power rule for logarithms, that 2 will come out in front. So we'll multiply that by 8, so that's going to be 16 ln of 2 plus 8 ln of 2. Now we can combine the ln of 2's because those are the same number, and we're just going to perform the operation minus 16 plus 8. So 12 minus 8 ln of 2, and that's your answer. So not too bad. All right. So in this case, we had to find one left endpoint, and that wasn't too bad. But yes, it can get more complicated. So we're going to do yet another example. Okay, so we're ramping up the difficulty level here. Okay, so example. And here we're going to have to find points of intersection, and we get 2 integrals. All right, so the problem here is find the area bounded between y equals cosine of x and y equals 1 minus cosine of x over the interval, close bracket, 0 to pi. All right, so let's sketch this before we do anything else. So I'm going to have here my coordinate plane. Looks good. And then down here, looks good. So my first curve, cosine of x, right? Remember that cosine starts at a peak and between, so let's make this pi over 2. Let's make this pi. Okay, so we're going to end right here. This is our right boundary. And cosine of x between 0 and pi just decreases the whole time. So it's going to look like this, crosses the y-axis there, and then it reaches 1 there, or -1 there. That's roughly what it looks like. So that's y equals cosine of x. As for 1 minus cosine of x, so two things are happening there. First, shifted up by 1, and it's reflected across the y-axis, okay? So we know that if we reflect it, that'll look like this. And I'm going to erase the work that I'm doing here in a second, but if I reflect it, it'll look like this. But then if you move it up by 1, then it should look like this. Not the greatest graph in the world, but it'll do. All right, so now I can erase this. And the important part here now is if I'm looking at the area bounded between the two integrals, so first of all, they intersect at some point here that I don't know. I don't know what this point is yet, okay? So I'm going to need to find that point, and I'm going to call that A. Also, if I look at the infinitesimal slice of the areas for both, here's the first infinitesimal slice, here's the second infinitesimal slice. Notice that which one we consider the upper curve changes. So for the first one, the infinitesimal area that we're looking at is going to be cosine of x minus 1 minus cosine of x dx. And then between 0 and a. And the second infinitesimal slice has an area 1 minus cosine of x minus cosine of x dx. So those are flipped. So we need to set up two integrals regardless because of which curve comes first. All right? So step 1, then, find the point of intersection. Okay, so we need to find where f of x equals g of x. So we're going to solve the trigonometric equation. Cosine of x equals (1 minus cosine of x). Move the cosine of x so you get 2 cosine of x equals 1, which means cosine of x equals 1/2. Now, this has infinitely many solutions because cosine of x is periodic. It's 2 pi periodic. But we are looking at the range between 0 and pi. So x is between 0 and pi. So we are only looking for one value here, and that is going to be pi over 3. That's our A. So that means our full area, so if I'm going to call this area 1, area 2, the area then is area 1 plus area 2, and I have two different integrals for those. So I have the integral from 0 to pi over 3 of, now remember that infinitesimal slice, that's this one right here. So cosine of x minus 1 minus cosine of x dx plus the integral from pi over 3 to pi. So remember, those are the bounds for the second integral because I'm starting from a and ending at pi. And that's going to be 1 minus cosine of x minus cosine of x dx. Okay, that is our integral. So I'm going to clean this up a little bit, and then we're going to actually do the calculation now. So continuing from the previous page, if we clean this up, this should be 0 pi over from 0 to pi over 3, the integral of 2 cosine x minus 1 dx plus the integral from pi over 3 to pi of 1 minus 2 cosine x dx. Okay, so now how do we integrate this? So remember that we can pull the 2 out from the cosine of x, and the integral of cosine of x is sine of x. So simple sine rule. So remember, I'm going to put that over here on the side. So remember that the integral of cosine is sine. And so we will get 2 sine of x minus x, ranging from 0 to pi over 3, plus x minus 2 sine of x from pi over 3 to pi. And we're hoping that some cancellation will happen here. We're not guaranteed that. But let's just go ahead and do the calculation then. So we're going to get 2 sine of pi over 3 minus pi over 3 minus 2 sine of 0 minus 0. The nice thing here is that that will cancel out to just 0, so we won't have to worry about that part. Plus, I'm going to put that on the second line here. I'm going to have pi minus 2 sine of pi minus pi over 3 minus 2 sine of pi over 3. Okay, so some helpful things here. First of all, this goes away because sine of 0 is 0 and 0 is 0. Duh. Pi, can't do anything about that, but sine of pi is also 0. Thank goodness. It goes away. So now we can just focus on collecting like terms, and then once we have that, we'll figure out what sine of pi over 3 is. So 2 sine of pi over 3, and then notice that there's a double negative sign here, so that we're actually going to add. It's going to be 4 sine of pi over 3, and then minus pi over 3, and then another minus pi over 3. That's going to mean minus 2 pi over 3, and then lastly plus pi. Okay? So important things here are sine of pi over 3 is actually root 3 over 2. So we get 4 times root 3 over 2. So that's what this became. And minus 2 pi over 3 plus pi gives us plus pi over 3. And our last step is to clean this up just a tiny bit more. The 4 and the 2 will give us a 2 in the numerator. So 2 root 3 plus pi over 3, that is actually our answer. And we're done. So that's the area. So as you can see, there's some, it can ramp up in difficulty. And in a future video, we're going to be talking about the area between two implicit curves, which also will make this significantly more interesting. But then with that video, we'll wrap up.